Good afternoon everyone, I am Mr. Thank you for joining me for this video where we are looking here at a single difficult question. A second order non-homogeneous or inhomogeneous differential equation has to be solved. It's inhomogeneous or non-homogeneous because your equation here is not equal to a zero. It's equal to a bunch of items. You know, based on the videos I presented, we've seen equations like this, but they've equaled a linear item, a constant, a quadratic factor, trigonometric, exponential. But look here, we have a combination of items. This item, everything being equal to a certain function here, is equal to a certain bunch of items. You have a linear item. What is that linear item? I have an x. We have an exponential item and it's e to the x. Then we have a trigonometric item here and it's cosine 2x. So how do we solve a differential equation where you have a lot of this going on? Well, you know, solving the complementary function is easy. It's the particular integrals which are difficult. You will determine the number of particular integrals which are needed, and there are two over here. One for these two items which are in the product and one for this item over here. The number of items you see clearly separated will determine the number of particular integrals which will add to your general solution. Your general solution is going to be equal to a complementary function which will come from right here plus a certain particular integral, we'll call that 1. It's going to come from right here, and plus another particular integral coming from right here 2. So there's a bunch of items, hence the complexity is difficult. What we can do over here is look at this complementary function first. It's easy. When you're looking at this, you know the procedures. Then you would plug these items in here. You will have here 2r squared e to the rx plus 3r e to the rx minus 2 e to the rx is equal to 0. You could literally isolate the exponential terms, take them on the other side, divide them by 0, and they'll go away. What you really have is a 2r squared plus 3r minus 2. When you factor this out, what do you have? You have over here 2r and an r, and since you have a positive 3r, you'll have here a plus 2, and here you'll have a minus 1. Think about it, 2r squared plus 4r minus r, that'll give you a 2r squared plus 3r, then you'll have your minus 2. But you've determined your factors, now determine your solution. R here is equal to solve for r. From both of these factors you have 1 over 2 and minus 2. I will not write the complementary function right away because I need space for these items here. They're lengthy. So we'll write over here r was equal to 1 over 2 and minus 2. Then we'll bring it into our complementary function at the end. You know the complementary function template is easy. Our challenge is this right here, the particular integrals. We've determined our complementary function items. Let's go to the particular integral. Our first particular integral, which I've written here, pi1, is going to come from x e to the x. You are seeing over here a linear term x in a product relationship with an exponential term e to the x. What should be our basic template we use over here? You know, when you're looking at a linear term, it is always ax plus b. That's your linear term. If you had a quadratic term, you'd be looking at ax squared plus bx plus c. If you had a constant term, you'd just be looking at a. But we have a linear term, ax plus b. But now, how do we marry it up with the exponential term? Our exponential term here is not too hard. You have a product over there in your equation, therefore you will have a product over here. And this is what we will use for our template. My y, my particular integral, my test function is equal to this, ax plus b exponent ex. Now let's do the derivative of this. It's not difficult. You're going to do the product rule over here. My derivative, first order derivative, is exponential times the derivative of this, which is e to the x times a, plus this times the derivative of that, which will be ax plus b times e exponent x. The product rule of derivatives. Open everything up. When you open it up, you'll have e to the x a plus e to the x xa plus e to the x b. But I'm going to write this in a better way, because I would have the constants first, the functions later. If I were to isolate the exponential over here, I'm looking here at an e to the x, then I have a plus ax plus b. This right here is my first order derivative of that item. Now what I'm going to do is I'm going to take this item and put it over here only because I need space. I'm going to transfer this right over here. We have e to the x, a plus ax plus b. This right here is my first order derivative. Now we have to find the second order derivative, and let's do it. Second order derivative of this or the next derivative of that, and it's not too hard. You're going to run that through the product rule. Here's your one function, here's your other function. This times the derivative of that would be a plus ax plus b times the exponential plus this times the derivative of that, which is exponential times a. When you open this up and you compute it all, you have e exponent x a plus a x e exponent x plus b e exponent x plus a e exponent x. When you combine all the common terms, what are they? You have these. And this right here is a standalone term, this right here is another standalone term. From all of these, if you were to isolate the exponential, what will you get? You have a plus a, you'll have a 2a plus ax plus b. Remember, you can work this out on the side. There's nothing here which is inordinately hard. You just have to work this out on the side, but it should be right. My template, which I'm using for my particular integral 1 to determine for this right here, is this. Then I'm doing the first order and the second order derivative of that function right there using product rule of derivatives. Now all of these have to be plugged in. So we've created space over here. Now we have to find the values of these items a and b. We're still working here on the particular integral 1. There'll be two, one coming from here and one coming from there. We're going to plug all of these items. Here's my 0 order, first order, second order right over here. I'll do 2 times all of this. When I do 2 times all of that, and I'll open it up. And we can do this, much of this mentally, but we'll open it up. We'll have 2 times this 2a is a 4a. So we will have over here 4a e exponent x, and I'll do 2 times that with the exponential. I'll have plus 2a x e to the x. Then I'll do 2 times this with the exponential. I'll have plus 2b e to the x. Hence it's complex because there's too much going on. Now I'll do 3 times everything from right here. I'll open this up and I'll do times 3. And when we do it, we'll have 3a e to the x. 3a e exponent x. Then I'll do 3 times the product of these items, which will be 3a x e to the x, then 3 and then b e x plus 3b e exponent x. Now we'll put a minus over here because we have a minus 2 multiplying with everything over here, everything here. I'll have a minus, I'll open this up and I'll multiply with a 2. And we won't forget the minus. We'll have here a minus 2a x e to the x minus 2b e to the x. All of this is equal to this, x e to the x. What do we do over here? Let's look for our common terms. I have my ax terms, ax, ex, and let's combine those. I'm looking at this item right over here. I have this item here and this here. Positive 2 minus 2 cancel out. I have here a 3ax e exponent x is equal to, here's a term which it equals because they look similar. You have a linear and an exponential x e to the x. Let's look at my other terms. I have a 4aex plus 3aex. I have here 7aex, and it does not have a corresponding term after the equal sign. Let's look at my b exponential terms. I have a positive 2b minus 2b, they cancel out, plus 3bx. Then I have a 3bex. It doesn't equal to anything. When I'm looking over here, this equals to that. You can literally cancel these out and it's equal to 1. Here a is equal to 1 over 3. So we're seeing here a is equal to 1 over 3, and that looks good. Now we have to solve for b. Look over here at these two terms. These two terms are in a positive relationship based on what you see over here, but they're not equal to anything here because you have no corresponding term. They're equal to 0. That's what they are equal to. If you isolate the exponential and take it onto the other side, it zeroes out. Isolate the exponential from here, take it on the other side, get rid of it. You are looking at a 7a plus 3b is equal to 0. Push this a right over here. You have over here 3b is equal to 7 over 3 going on the other side, minus 7 over 3, and then b is equal to minus 7 over 3 divided by 3. You know what that is. That's a minus 7 over 9. So I know my b is equal to minus 7 over 9. Let's clean everything out and then we'll bring these two items right here into my template and we will have determined our first particular integral. When I bring these values right over here, I'm looking at my first particular integral is equal to what? I have here x over 3 minus 7 over 9. But I want to separate them out because I don't want to present my final general solution with this. I'll separate them out. I'll have here x e to the x with a 1 over 3. Multiply this with exponential and bring in the value of a. 1 over 3 x e to the x. That looks good. Now multiply this with this and separate them out. I'll have here a minus 7 over 9 e exponent x. This right here is my first particular integral and it's done. 1 over 3 x exponential minus 7 over 9 exponential, but you can see it's a difficult procedure because we have here a linear and an exponential term. It becomes complicated. We haven't forgotten about these two values. We'll work on those at the end. Let's look here at my second particular integral, which is to do with that. Y here is equal to something, but it should mirror that. What will you use as a template when you're looking at trigonometric items? You'll use c cosine x plus d sine x. But this is not 100% accurate. We have a value here, constant. You have to bring it in. We will have y is equal to c cosine 2x plus d sine 2x. This right here is what I'll use. Now my first order derivative will be the derivative of this. We will have coming from here minus 2c sine 2x. Then from here I'll have a 2d cosine 2x. Now we have to do the second order derivative, and the derivative of this, not too hard, it'll be minus 4c cosine 2x, and then from here we'll have a minus 4d sine 2x. Now we have to bring these items right over here, and again it's complex because it's lengthy. Bring these items into play. I have a 2 and a double order which will multiply with this. I'll have here a minus 8c cosine 2x. Then I'll have here a minus 8d sine 2x. Then 3 with all of this item over here. What will we have? We'll have here a minus 6c sine 2x. And then 3 with the other item over here. Plus 6d cosine 2x. And then lastly minus 2 with the y terms. Minus 2c cosine 2x. And then minus 2d sine 2x. So you can see all of this is equal to one item right here, cosine 2x. Now we have to start working on this. I have 1, 2, 3, 4, 5, 6 items. We have to work on them. And how can we work on them? We will isolate. I'm going to create a little bit of space right here in the middle. You know that this right here is our template right over here. I'll erase the first and the second order derivatives and I'll work over there. So what do we do from here? We're going to look for our cosine 2x terms, and we're going to look for our sine 2x terms, and we have to isolate the items that are involved with them. My cosine 2x here has a minus 8c. Here my cosine 2x has a plus 6d, and here my cosine 2x has a minus 2c. My sine 2x terms has a minus 8d, and again it's lengthy and it's complex. My sine term here is a minus 6c, and here I have a minus 2d. Now when I look at these items I can simplify them. I'm erasing all of this because I know everything is good as I need space. I have over here, after I simplified cosine 2x, minus 8c minus 2c is a minus 10c plus 6d. Then I have a sine 2x. This right here is systems of linear equations. I have here a minus 6c and then a minus 10d. That's what I have. How do I know what they equal? I have a cosine 2x term. The coefficient over here is equal to 1. This cosine 2x term has an equal to a 1 cosine 2x. There's no corresponding sine 2x term. There isn't any here, so you can make it equal to 0. Now we have our systems of linear equations. You're only focusing on the coefficients. I have here a minus 10c plus 6d is equal to 1. And then for the sine 2x terms, I have a minus 6c minus 10d is equal to 0. You have to do systems of linear equations. If you do the systems of linear equations, it's not hard by any means. You can multiply this top term here by a 3. You can multiply this by a minus 5. What do I have? I'll have here a minus 30c plus 18d is equal to 3. Here I'll have a 30c positive 50d is equal to 0. These will cancel out. I'm adding them up. I have here a 68d is equal to 3, and d here is equal to 3 divided by 68. Now we have to find the c term, and we can just pick any of these equations and solve for c, and it's easy. My equations are right over here, minus 10c plus 60 or minus 6c minus 10d. I'm picking the one which is equal to 0. I'm looking here at this equation right here. I'm going to plug in d. I have a minus 6c minus 10 times 3 over 68 is equal to 0. I'm solving for c. Push the negative term on the other side, it becomes a positive. I'm looking here at a 30 over 68, and then c is equal to, push this on the other side, it will divide, minus 1 over 6. This goes in here 5 times, c is equal to minus 5 over 68. Minus 5 over 68. Now we have everything we need to put in this form right here, and let's do it. We will publish our particular integral for you all, then we'll bring everything into a general solution, and we will be done with this question. My particular integral number 2 right here is equal to, in this form right here, I have a c and a d. I have a minus 5 over 68 cosine 2x plus d, 3 over 68 sine 2x. Now we have everything to publish our answer. Everything has been cleaned out for you. We have our particular integral 2, we have particular integral 1, we have the items for our complementary function. Our general solution here is equal to a complementary function plus particular integral 1 to correspond with that part plus particular integral 2 to correspond with that part. Let's publish our answer. Our general solution is equal to, remember the template for these roots. You have two real roots. It'll be a e exponent x over 2 plus b e exponent minus 2x. You have two solutions here. You have a second order differential equation, therefore you must have two arbitrary constants, and we have that 1 over 2x minus 2x. Here's our complementary function. Let's bring in our particular integral 1. I have here a 1 over 3x e to the x minus 7 over 9 e exponent x. Let's bring in this second particular integral. Everything is in a sum format, everything adds. Let's bring in these items over here. I'm not going to add it over here so we run out of space. I'll bring that item right here in the next line, minus 5 over 68 cosine 2x plus 3 over 68 sine 2x. That right here is our answer. I'm cleaning it out so you can see it clearly. So everything has been cleared out, and here's our general solution. A times e exponent x over 2 plus b times e exponent minus 2x, my complementary function, plus 1 over 3x e exponent x minus 7 over 9 e exponent x, my first particular integral for this part, minus 5 over 68 cosine 2x plus 3 over 68 sine 2x, this right here, corresponding with this part right here, and we are done. Here is our non-homogeneous differential equation solved. It's hard, it's lengthy, and it's arduous work, but it is right and it should be good. Have a good day.